welcome back to the channel. I hope you guys are doing good. So we will see today's daily challenge and we will try to solve it together. So this is definitely an intuitively hard kind of problem, but the coding this will be really simple. So we will spend a lot of time in understanding the problem and analyzing its various cases, and the coding portion is very simple. It's just 3 to 4 lines. So let's see. Minimum 1-bit operations to make integer 0. Given an integer n, you must transform it to 0 by using the following operations any number of times. Change the rightmost 0th bit in the binary representation of n. Okay. Change the ith bit in the binary representation of n if the I minus 1th bit is set to 1 and I minus 2 till the 0th bit are all set to 0. Okay. Return the minimum number of operations to transform n to 0. So you need to transfer from a number n to 0. You can see what it is told. The first operation is very simple. It is just that if you are given a large number, you can change the last bit. You can flip the last bit. So in one operation, just you can change this 0 to 1. And again, if you are given some other large number, you can change this bit. So you can change this ith bit if the I minus 1th bit is 1 and all the bits after that are 0, you see. So you can change in one operation. If this is true, then you can in one operation change this to this. Okay, so that is what the both operations are telling you to do. Okay, I hope you do get an idea of what we need to do exactly in the problem, and yeah, you can start thinking it right now. And you see, you try to visualize this example of n equals to 6. What will happen in this is that the binary representation of 6 is 110. Now you need to convert it to 0. So what you do is that you see 110. So it means that you see, if you talk of this being the ith bit, the I minus 1th bit is 1. Okay, the I minus 1th bit is 1 and all the remaining bits are 0 after that. So you can change this to, you can flip this bit with the second operation. Okay, and you see you got 1010, and after this what you can do is that you can flip the last bit to get 011 with the first operation. And yeah, similarly you can now flip this to be the, you can take this to be the ith bit and try to flip it with the second operation, and so on. Okay, I hope you do understand what I am trying to tell you. Okay, so first of all, let's try to visualize some cases of what will be our possible values for this. Okay, so let's see, let's take an example of, let's say, 2 to the power 0. First we will see, if you try to form any number n, you know you can just form it by summations of 2 to the powers. Okay, I hope you already know this. So let's try to visualize, or any number you can convert it into binary number and try to remove one by one the ones. Okay, so we will try to visualize what will happen if we try to change this one to 2 to the power 0 1. If I try to change this number to 0, how many operations will I take? You see, I can just flip this last bit and make it 0. So I took just one operation for this. Okay, now you have 2 to the power 1, which is nothing but 2 into the binary representation is nothing but 10. So how you can change this? So one thing you can do easily is that convert it to 1 1 first by changing the first bit, and then you do something like change this bit to 0 1, because this is the ith bit and this is the I minus 1th bit, which is 1, and all the other bits which is not even present there. So you can do this, and you can simply flip the last bit to make it 0. Okay, so yeah, how many operations you took? This is one operation, this is one, this is one. So you took 3 operations, right? And that is very simple. See, you took 3 operations. What about 2 to the power 2, which is nothing but 4? If you write that in binary, it will be 100. Now how will you change this? Okay, so you try to fidget this with by your own. Okay, so yeah, you will get something definitely. You see, what you can do is that let's say convert this to 101, and then what you can do is change this to 111. Okay, change the middle bit, because yeah, I hope you do understand. You can flip this bit. If the I minus 1th bit is 1 and all the other bits are 0, all the other bits are not present only, so you can consider them whatever you like. And you see, what you can do in this case, you can flip the last bit whenever you want. So this first bit, 0th bit, you can flip it whenever you want. So you choose to flip this in the operation, first operation, by taking this. Okay, now you see the first bit was there for so long. You can now choose to turn off this first bit. How? You see, this is the ith bit and this is the I minus 1th bit, which is 1, and all the other bits are 0. So definitely you can choose to convert this from 0 1 0. I hope you do understand. I am just using either this operation 1 or operation 2 to convert this. Okay, now you see what you can do in this case is that you can convert this to 1 1, and then again you can convert this to 0 1, and you can again convert this to 0. Okay, so yeah, that you can do easily. And how many operations you took? You see, let's count. It will be 1 2 3 4 5 6 7. You took 7 operations for this, right? Okay, so far so good. Now what if I go to an even larger number? I will take an enormously large number of operations. Let's try to solve for 2 to the power 3. It is nothing but 8. Okay. So what are all the things which you can try here? Try this out. Okay. So let's see. What you can do is that you can, let's say, transfer this to 0 1, and let's say after this what you can do is uh, try to transfer something like this, and yeah, and then what you can do is change the first bit again. So why did you change the first bit? So that you can now flip this bit, because I minus 1th bit is 0, I minus 1th bit is 1, and all the other bits are 0 from here. So you can choose to flip this bit now. Okay, yeah, so you are having that, and you see, after that you can flip the last bit. Then what you can do, uh, see which bit you would want to flip. Now you can flip this bit, right? So 1 1 0 1, and the last bit you can flip whenever you want. So again you choose to flip this bit. Okay, now you see what you get in one operation. Now you can just flip this bit, because this is the ith bit and I minus 1th bit is 1 again, and all the other bits are 0. So you are using operation 2 again to flip this bit. Okay, so you can get a 0, you can get a 100. Okay, so you see, once you get 100, 100, not, it's not 100, it's 4. Okay, so you can follow these same steps, the same step which you started to from 100 to convert it to 0. You can follow the same step again for this. Okay, so once you have got till 100, you can just follow the same step, and you can tell that you can take 7 more steps. So what is the number of steps taken here? 1 2 3 4 5 6 7 8. 8 plus 7 is 15. Okay, so you basically took 15 steps for this. And yeah, uh, so let me just write this in 15. Okay, so one pattern you definitely observe, that first of all, that it is some recurrence relation. It is some recurrence relation, because see, if you want to convert a higher power, you can convert it to a lower power and then follow the recursive pattern. So if you want to change 2 to the power 2, which is nothing but 100, you can just convert it to 100. You can first convert to 10, and then you follow the same pattern which you have been following earlier. Similarly, for 1000, you can first convert it to 100 and then follow the same pattern which you have been following earlier. So first of all, the recurrence is the way. Recurrence relation, so it comes, so the basic idea which comes is that you can follow a recursive pattern, and whenever you think this, find the exact recurrence relation for this. Finding the exact recurrence relation will be the idea. Another idea which you get is that first of all, this is your first observation. Okay, so this was your first observation, let's say. And what is the second observation? You see, if you want to convert 2 to the power k to 0, how many operations you need? So let's say you want to convert 2 to the power 2 to 0. So you take 2 to the power 2 to the power 3 minus 1, 8 minus 1, 7 number of operations, right? Similarly, if you want to convert 2 to the power 3 to 0, you need 15 operations. It means that 2 to the power 4 minus 1. So if you want to convert 2 to the power k to 0, number of operations which is required is nothing but 2 to the power k plus 1 minus 1. Okay, so I hope this much is very simple to understand. So in order to convert a 2 to the power k to 0, you get 2 to the power k plus 1 minus 1. Okay. What is the third observation? And it is a very important observation. Okay. It is a really important thing which you need to observe in this thing. Can you tell me? Can you tell me what is that observation? Try to think. So you see, let's say consider a 3-bit number. What I'm trying to say is that consider a 3-bit number, any 3-bit number. So it will have 3 bits. That goes without saying. Okay. Among all of these, which takes the largest number of operations? You see, if I try to convert, if I tell you to convert this to 0, how many operations you just now took? You took 7 operations, right? You will tell me that the answer is 7. Okay. But if I tell you convert this 111 to 0, how many operations you will take? You see, you just took 1, 2, 3, 4, 5 operations. See, although this is a large number, are you understanding what I'm trying to say? Although this is a large number, number is 7, and this number, what is this? It is nothing but 4. Although this is a large number 7, in order to convert a large number to 0, you are taking less number of operations. So basically, when you are converting, and so the third observation is nothing but when you are converting an n-bit number to 0, okay, you are going through all the n-bit numbers. So you do get it, right? What I'm trying to say, all the 3-bit numbers. See, when you are trying to convert this 100 to 0, all possible, most of see the 3-bit numbers you are getting. Okay, so you are getting this also. You are getting 5, you are getting 7, you are getting 6. Okay, you have this 4. So 3-bit numbers you are getting all of them in order to convert to 0. I hope you do get what I'm trying to say, right? And they differ by just a single bit. So if I try to tell you that you have a large number, so can you tell me, see, you have, let's say, a large number. Okay, now you want to convert it to 0. You can convert it to 0, right? Can you divide this number into something like this number, which is in the form of 2 to the power k, plus some other number x, which is nothing but 1011010. Okay, and you can tell me that if you ask me to convert this 2 to the power k to 0, you will take more number of operation than you ask me to convert this to 0. Okay, so let f denote our function, which tells that f of dot tells me number of operations to convert a function dot to 0. Okay, so can you tell me number of operations? F denotes number of operations. It is as simple as that. So can you tell me, if I ask you a question, that any number, first of all, any number n, it can be written in the form of 2 to the power k plus x, and x is a number which is obtained by removing the largest bit, and you can simply apply a recurrence relation by taking this as 2 to the power k plus x. Okay, for the next recursive pattern. Okay, so what I'm trying to do is that trying to find some relation for this. So let's say you want to take any number to the power k plus x, you want to convert this number to 0. Okay, f is the number of operations which you need to convert this to 0. You will tell me that this is less than f if you want to convert 2 to the power k to 0. Okay, so I hope you do understand what I'm trying to do. Is that this number, although it is small, but it takes a large number of operations. Okay, now if I try to tell you, if I try to tell you what is the value of this, if you want to do this, see, if I want to transfer this number to 2 to the power k, that is, I want to remove this x bit. This is same as transferring x to 0, number of operations taken by x to 0. Okay, so essentially, to balance this inequality, and convert this to a equality, this is the term which is missing. It is the term which is missing, right? So easily you can tell me that 2 if you want to convert this to 0, this is the number of operations which you take to convert this to 0. Okay, and you add this value to f of x to 0. This is nothing but this only. Okay, so what you can do, what is the final recurrence relation which you get, is that if you want any number n, this was the any number n, right? This was the any number n. If you want to convert that to 0, just apply this recurrence relation, minus f of x transferred to 0. So this is the recurrence relation which you need to apply. Okay, and what is this number exactly? What is this number? You are telling me that it is a recurrence relation, but how exactly? So you see, if this n is a number, as I told you, let's say it is a number like this. Okay, if n is a number like this, then what is this x? X is nothing but this, right? So you removing the topmost bit, so you just remove the topmost bit. Now I hope you already know that how like what is the what is the most powered bit is this one. Okay, so you can easily get by taking a log, if this is n, and take a log base 2 of n and write the floor value of this. Okay, so I hope you do understand what I'm trying to say. If you, this is basically I'm trying to count number of bits which are present here. So what 111 is 7, so if I take log base 2 of 7 and convert it to steel, so first of all log base 7 will be 2 point something, right? And it will be, steel will be just 2, so it will tell you that this is the 2th bit, this is the 0th bit, this is the first bit, this is the second bit. Okay, so in this way you can just get it done. Okay, so I hope you do understand what I'm trying to do. I will just simply write a recurrence relation. Okay, so what will be my steps? So first of all, I will write a base case that of the recursion will be that if n equals to 0, you can simply return 0. This will be the base case. And what I can do, you see, uh, I can try to find first the k value, right? I can do what is that floor of k and log 2 of n. Okay, so this will just give me what uh, like what number of bit I need to make it 0. Okay, and you know how to make a bit 0, you can just perform a XOR with that. Okay, so let's say if I try to tell you reset the bit, so you have an ith bit. Okay, let's say you have an ith bit which you want to reset. Let's say this is the ith bit. What you do, you do a XOR operation with this. You do a XOR operation with this. What you get? 1100000. So in order to unset the bit, unset a bit, you need to perform a XOR operation. How you perform the XOR? If you unset the ith bit, you perform a XOR with one left shift I, one left shift I, XOR with that number. Okay, so you can just do that. I hope you do get it. And yeah, for this, now you see, if I tell you return, see what was my recurrence relation for this, what do you need to do? Find the number of operations taken by 2 to the power k. Now 2 to the power k, what was the number of operations we derived? It was 2 to the power k plus 1 minus 1. Okay, so our second observation. So basically here I can replace this term by 2 to the power k plus 1 minus 1 minus with f of the next recurrence relation. Okay, so 2 to the power k plus 1 minus 1. So yeah, so how will I calculate this 2 to the power k plus 1? So yeah, I can just calculate, let's say, an operation OP, which is needed to convert 2 to the power k to 0. So 2 to the power k plus 1 minus 1. So this is not the operations to convert 2 to the power of k to 0. Okay, and what you can do is that operations, number of operations, minus what is the formula which we got, minus this x to 0. How this x is to 0? See, this function converts the n to 0, right? So I can write this same function, as I'm trying to do a recurrence relation. I can choose to write this same function, and instead of n it will be x to 0. Now how will we get this x? This x is very simple. This x is obtained by the XOR by the XOR operation. That is, you need to remove the, you need to switch off the first bit. You need to switch off the most significant bit. Now this is the most significant bit. Most significant bit. Switch off the most significant bit. Okay. So how will you switch off? You can definitely do it by using a XOR operations. Okay, so X I can just simply replace by 1 left shift of K. So yeah, I am here applying recurrence, which I derived, and n left shift of K. What I'm doing is switching off the most significant bit. Why? Because as I have already told you how I am exactly solving the problem is that by writing 2 to the power k plus x as 2 to the power k plus x actually, right? So if this is 2 to the power k and this is 2 to the power x, okay, so then this is my whole number n, which is 2 to the power k plus x. Okay, that's how I am doing. And for in order to get x, as you can see, I am just switching off my most significant bit. So yeah, that's what I'm doing. I'm switching off my most significant bit and applying the recurrence lesson. That's all. It's a simple 4 lines of code, and you can just simply submit it. I hope it will work just fine. There should be no error in this. Yeah, if you try to submit it for all test cases also, it will just work fine, because it is a simple recurrence relation. And you see, mm, if you are thinking that, hey, why not TLE, because n is 1e9 and 1e9 means it is a 31 bit number, so 31 times recurrence relation is you can easily run, and you see the time complexity is 100% bits.